I want to start this one exactly the way I started our conversation about extra dimensions, because I think the pattern of misleading titles versus honest physics deserves the same careful treatment every time. CERN has not detected a hidden universe, no confirmed signal, no enhanced discovery, nothing that any serious physicist working on this problem would describe as detection in the way that word is normally used in experimental physics. What I want to walk you through instead is something genuinely fascinating in its own right. Why some of the most careful, most rigorous experimental physicists working today have spent years actively searching for exactly this kind of hidden sector, what specific experiments they've built to look for it, and why the honest current state of that search is closer to systematically ruling things out than to finding anything. Let me begin with the problem. This entire search program exists to solve, because I think understanding the motivation matters more than the specific experimental details, at least at first. Astronomers have known, since observations made throughout the 20th century and refined dramatically since my own death, that the visible matter in the universe, stars, gas, dust, everything that emits or absorbs light in ways our telescopes can directly detect, simply isn't enough to explain how galaxies actually behave gravitationally. Galaxies rotate at speeds that should, by ordinary Newtonian gravity applied to their visible mass alone, tear themselves apart, with stars in the outer regions flying off entirely rather than remaining gravitationally bound in the orderly rotating disks we actually observe. Galaxy clusters show similar discrepancies, and the large-scale structure of the universe itself, the way matter clumped together into the filaments and voids we observe on the largest scales, requires considerably more gravitational influence than visible matter alone provides. The explanation astronomers and cosmologists settled on, developed gradually through the latter half of the 20th century, is that some form of matter exists that interacts gravitationally exactly as ordinary matter does, but doesn't interact with light or with the electromagnetic force at all, making it completely invisible to every conventional telescope, however powerful. This invisible substance, now called dark matter, appears, based on the most precise current cosmological measurements, to outweigh all the ordinary visible matter in the universe by a considerable margin. Current estimates suggest dark matter constitutes roughly 27% of the universe's total mass energy content, compared to only about 5% for the ordinary matter that makes up stars, planets, and everything we can directly observe. I want to be honest that dark matter's existence, inferred entirely through gravitational effects, represents one of the strangest and most persistent open problems in physics. A substance we're confident exists, based on overwhelming and consistent gravitational evidence gathered across many independent lines of observation. But that has never once been directly detected in any laboratory, despite decades of dedicated, increasingly sophisticated search efforts. This is where the specific research program the title alludes to actually enters the story, and I want to walk through it carefully because it involves several genuinely distinct theoretical ideas that sometimes get blended together in popular discussion in ways that obscure how they actually relate to each other. The most straightforward category of dark matter search, pursued for decades using various techniques, looks for what are sometimes called WIMPs, weakly interacting massive particles. A hypothesis suggesting dark matter consists of a new, heavy, fundamental particle that interacts with ordinary matter only through the weak nuclear force and gravity, interacting so rarely and so weakly that it would pass through ordinary matter, including detectors built specifically to catch it. The overwhelming majority of the time with only very occasional, extraordinarily faint interactions available to be caught. Decades of increasingly sensitive WIMP searches using detectors buried deep underground to shield them from other sources of background radiation have failed to find any confirmed WIMP signal, progressively ruling out larger and larger portions of the theoretically plausible parameter space for what a WIMP's mass and interaction strength could actually be. This persistent absence of a WIMP detection, despite the enormous sensitivity these underground detectors have achieved, has pushed a significant portion of the theoretical physics community toward a different, and in some ways stranger, category of hypothesis. The idea that dark matter might not simply be a single new heavy particles interacting weakly with our own familiar particles, but might instead belong to an entirely separate collection of particles and forces, one that interacts with our own familiar matter only extraordinarily weakly, if at all, except through gravity. This broader idea goes by several related names in the physics literature: a dark sector, a hidden sector, or in one particularly evocative version of the theory, a hidden valley. I want to explain the hidden valley concept specifically because I think it captures the underlying idea in a genuinely illuminating way. Imagine our own familiar matter, quarks, electrons, the force carriers of the Standard Model, as existing on top of one particular mountain within a landscape of possible particle physics theories. The hidden valley hypothesis proposes that there might be an entirely separate valley elsewhere in that same landscape, containing its own rich collection of particles and its own forces, potentially even its own version of something analogous to nuclear physics or chemistry, operating according to entirely different rules from our own, connected to our familiar Standard Model matter only through some extraordinarily weak, narrow, connecting passage, a mathematical bridge physicists call a portal, since it represents the only way information or interaction could pass between the two separate sectors. Several specific candidates for what this portal connection might actually consist of have been proposed and are being actively searched for in real experiments right now. One of the most actively pursued is called a dark photon, a hypothetical particle that would function within this hidden sector, analogously to how an ordinary photon mediates electromagnetic interactions within our familiar Standard Model, but that could, through an extraordinarily weak coupling, occasionally interact with and briefly transform into ordinary Standard Model particles, providing exactly the kind of narrow, rare bridge the portal concept requires. CERN operates several real, ongoing experiments specifically designed to search for exactly this kind of signal, and I want to walk through a couple of them directly because I think understanding the actual experimental design helps clarify both what's being searched for and why no confirmed detection has yet emerged. FASER, standing for Forward Search Experiment, is a relatively compact detector installed along the beamline of the Large Hadron Collider, positioned specifically to catch extremely weakly interacting particles that might be produced during the LHC's proton-proton collisions, but that would otherwise pass straight through the LHC's larger primary detectors without leaving any signal, precisely because they're hypothesized to interact so rarely with ordinary matter. FASER's most recent published results from a search completed and reported in early 2026 looked specifically for dark photons within a particular range of possible masses and coupling strengths. And I want to be direct and honest about what they actually found. 0 events matching the signature they were searching for. This null result allowed the FASER collaboration to set what physicists call exclusion limits, rigorously ruling out, with high statistical confidence, a specific, previously plausible region of dark photon mass and coupling strength as the explanation for dark matter, narrowing the remaining theoretically viable possibilities considerably. Without confirming any actual detection, I want to emphasize how genuinely valuable this kind of result actually is, even though it represents a null result rather than a discovery. Because I think this connects to something important about how careful experimental physics actually functions. Something I understood deeply from my own experience overseeing extraordinarily precise theoretical calculations that needed experimental confirmation before anyone could trust them. A null result from a sufficiently sensitive, carefully designed experiment doesn't mean nothing was learned. It means a specific previously viable hypothesis has been tested directly and found not to hold. At least within the specific range of parameters the experiment was sensitive to, systematically narrowing the space of remaining possibilities that future, more sensitive experiments will need to explore. A separate but related search, conducted using CERN's ATLAS detector, one of the LHC's two large general-purpose particle detectors, looks for a different, more indirect signature called soft unclustered energy patterns, or SOUP. Rather than searching for a single new particle directly, this search targets a specific, unusual pattern of energy deposits that certain hidden sector theories predict would result if a heavy, currently unknown mediator particle were produced in a collision and then decayed into a shower of many low-energy hidden sector particles, which would themselves eventually decay back into ordinary, detectable standard model particles, but in an unusual spherically symmetric pattern, quite different from the more focused, jet-like patterns typical of ordinary standard model particle production. The ATLAS collaboration's dedicated search for this specific signature, published as their first result of this kind, represents exactly the kind of careful, systematic search this entire research program requires, testing a specific, well-motivated theoretical prediction directly against real collision data, in this case also without yet finding a confirmed signal, but establishing a methodology and sensitivity that future data, particularly once the upgraded high-luminosity LHC begins operating, should be able to probe considerably further. I want to address the specific mirror universe concept the search results also surfaced, because I think it represents a genuinely distinct and interesting variant of this broader hidden sector idea, one that deserves its own careful explanation rather than being blended indiscriminately with the dark photon and hidden valley concepts I've already described. The mirror matter hypothesis, studied theoretically for decades but explored in some particularly interesting recent work by physicist Stefano Profumo and collaborators at the University of California. Santa Cruz, published in 2025, proposes something even more structurally specific than a generic hidden sector. It suggests that alongside our own familiar standard model of particles and forces, there might exist an entire parallel mirror copy of that same physics, a mirror version of quarks, a mirror version of the forces that bind them together, potentially even mirror versions of stars and other astrophysical structures, existing essentially as a shadow physics operating in parallel to our own, interacting with our familiar matter only through gravity and through the extraordinarily weak portal interactions I described earlier. What makes this specific proposal genuinely compelling as a candidate explanation for dark matter, according to the researchers who developed it, is that it doesn't require inventing an entirely new, arbitrary type of physics from scratch, because the mirror sector in this hypothesis would follow essentially the same fundamental laws as our own familiar standard model, just with its own separate set of particles. The theory has a certain mathematical elegance and internal consistency that some competing dark matter proposals lack. Profumo's specific 2025 work proposed that under this mirror matter framework, dense black hole-like objects could have formed within this hidden mirror sector during the early universe, through a process analogous to ordinary stellar collapse, but occurring entirely within the mirror sector's own physics, potentially accounting for all of the dark matter we observe today without requiring the WIMP particles that decades of direct detection experiments have failed to find. I want to be honest, in the same spirit of careful physics I've tried to maintain throughout every conversation we've had, that this mirror matter proposal remains, as of now, a genuinely serious but entirely theoretical framework, worked out mathematically and shown to be internally self-consistent, but without any direct experimental confirmation of its own. A separate, complementary experimental search conducted using CERN's NA64 experiment has specifically looked for evidence of ordinary neutral kaons, a known type of subatomic particle, transforming into their hypothesized mirror counterparts, a specific testable prediction this mirror sector framework makes. That search, published in 2025, set new constraints on how likely such a transition could be, without yet finding a confirmed signal, narrowing the theoretically viable parameter space in much the same way FASER's dark photon search did, without crossing the threshold into an actual discovery. I find myself thinking, considering this entire research program honestly, about how it compares to my own experience directing an enormous, historically unprecedented experimental effort at Los Alamos. Because I think there's a useful, if imperfect, parallel worth drawing. The search for a hidden or dark sector at CERN represents an extraordinarily ambitious undertaking, requiring multiple independent experiments, each testing different specific theoretical predictions, systematically working through an enormous space of possible particle masses, coupling strength, and interaction mechanisms, with each individual experiment's null result still representing genuine, valuable scientific progress by ruling out specific possibilities rather than simply failing to find anything interesting. What I think this current research program lacks, compared to my own wartime experiences, any comparable external pressure or deadline forcing a resolution within a specific time frame. The physicists searching for dark matter's true nature are engaged in exactly the kind of patient, systematic, decades-long experimental program that genuinely difficult physics questions often require, without the wartime urgency that shaped my own scientific work so profoundly. FASER continues collecting additional data and refining its sensitivity. Atlas's SUEP search represents only the first iteration of what will likely become an ongoing, refined search program as more collision data accumulates, and the planned Future Circular Collider, CERN's proposed successor to the current LHC, expected to begin operating sometime in the 2040s with construction on preliminary experiments like SHIP beginning around 2026, represents an even more ambitious, higher energy tool, specifically designed in part to push this same hidden sector search into energy ranges and sensitivity levels the current generation of experiments simply cannot reach. I want to close by returning directly to the question this title poses, because I think, as with our earlier conversation about extra dimensions, the honest answer captures something genuinely important about how careful experimental physics actually operates, in a way a simple yes or no would obscure. Has CERN detected the first sign of a hidden universe? Not in the sense of a confirmed discovery. Every specific experimental search I've described here, FASER's dark photon hunt, Atlas's SWEP search, NA64's mirror kaon search, has so far returned a 9 result, ruling out specific previously plausible possibilities without confirming any actual signal. What CERN has genuinely built and continues actively operating and refining is an extraordinarily sophisticated, multi-pronged experimental program specifically designed to search for exactly this kind of hidden sector, motivated by one of the deepest, most persistent unsolved problems in all of physics, the true particle nature of the dark matter that gravitational evidence tells us with real confidence makes up the overwhelming majority of all the matter in the universe. I think what makes this search genuinely exciting, even in the complete absence of a confirmed discovery so far, is precisely the same thing that made my own work on gravitational collapse exciting to me back in 1939, despite having no way at the time to know whether anyone would ever confirm it. We have a real confirmed problem. Dark matter's gravitational effects are not in serious scientific dispute, and a growing collection of increasingly sophisticated, increasingly sensitive experimental tools specifically designed to probe deeper and deeper into the range of possible explanations, systematically ruling out wrong answers while narrowing in on whatever the correct one eventually turns out to be. Whether that correct answer turns out to involve a hidden valley, a mirror universe, or some entirely different mechanism nobody has yet proposed, the search itself represents exactly the kind of patient, rigorous, genuinely open scientific inquiry that has always eventually been how physics makes its most significant discoveries, not through a single dramatic announcement, but through years of careful, systematic experimental work, each null result narrowing the path toward whatever truth is actually waiting to be found.